Hi everybody, I'm going to show how I go through kind of an unknown identification using NMR and IR. So I've got NMR peaks, proton and carbon, I've got the IR, and I've got the formula. Okay, so some of you are going to have to figure out this formula from a mass. I would say you're going to use a lot of the NMR to put that all together, and I'll kind of talk about that along the way. But since I have the formula, the very first thing that I'm going to start with is figuring out my degrees of unsaturation. So I have not made a video on degrees of unsaturation yet, but I'm just going to show you the way that I do it really fast. So I know that a saturated molecule, saturated, is going to be Cn and then H 2n plus 2. Okay, so that's the formula for a saturated molecule. So if I've got a situation where I've got 10 carbons, I can just go ahead and forget about the oxygens in this case. So I'll just figure out how much I would have if I had a saturated case. So it'd be 2 times 10 plus 2 would be 24. Wait, 22, sorry. I do know how to add it and multiply. So it'd be 22 saturated protons. And then from that, we're going to subtract the actual number of protons that we have, which is 12. And then all that divided by 2, that's going to give us 22 minus 12 is 10, divided by 2 is 5 degrees of unsaturation. Okay, so as soon as we see a degree of unsaturation that is 4 or above, we want to have our first thing in our mind go benzene? Question mark. Okay, because a benzene ring is going to be the most common way that you have 4 degrees of unsaturation, right? Because you've got the ring, that's 1, and then 1, 2, 3 pi bonds, that's a total of 4. Okay, so as soon as I see 5 degrees of unsaturation, I'm immediately thinking in my head, I'm probably going to be dealing with a benzene here, so I'm going to look for those things. All right, so then I go to my IR. So in the IR, I'm sorry that this is like not awesome looking. This is kind of old copies. So in the IR, the first thing that hits me is that guy, okay? That is screaming to me that it's some kind of OH peak. And then the fact that I've got this stuff, right, below 3,000, that's my sp3 C to H stretches. And then I don't really have anything in this big region, but I do have stuff right here. So I've got one that's a 1600 and one that's about 1700. So this one about 1700, that's going to be my carbonyl peak. Or at least what I'm assuming is going to be a carbonyl peak. As soon as I see something around 17, that's just what my mind goes to. And then this one right around 16, that's probably benzene again. Oh, that looks like benzene, or that's crazy. Okay, so now I have another piece of evidence that's kind of pointing me to might be benzene, right? Okay, so that's all I'm going to do from the IR. From that, I've seen, yeah, I've got an OH, I've got sp3 carbons, I've got a carbonyl probably, and most likely have that benzene. Okay, so the next thing that I move on to is the carbon. Okay, so I go ahead and I count the carbon environments. So in this one, we're just going to count up all of the peaks. Okay, the one thing that I will note here is that this proton, these two NMRs were both run in deuterated chloroform. And I think a lot of you are going to be running your NMRs in chloroform for the NMR lab, or you are given proton NMRs and carbon NMRs in chloroform. I'm not sure if you actually run them or not. But the things you want to keep in mind, this solvent for proton NMR, it's going to show up at 7.26. And for carbon, it's going to show up, and this is going to be, oh, I remember, okay, at 77. Okay, I have these off the top of my head, but again, you would be told what they are. So when we're looking through this little guy right here is solvent. And then this little guy right here is also solvent. Okay, so the 7.26 is a singlet. The 77 is actually 3 peaks. It is a triplet, but it's not shaped like a triplet necessarily, so they're all the same height. So it's like 3, 3, 3, all the same height. Okay. So once we've gotten the solvent out of the way, I'm going to count up the carbons here. So I've got 1, 2, 3, 4, 5, 6, 7, 8. So I've got 8 carbon environments. Okay, number of peaks equals number of environments. Okay, so when I compare that number that I've got 8 here to the fact that I've got 10 up here, that indicates to me not all of my carbons that are in this molecule have a unique environment. Some of them are equivalent to each other. Okay, so as soon as you put that together and you say, oh yeah, that number is less than 10, I have to have symmetry. I've got to have at least one plane of symmetry that's relating a couple of them. Okay, so we can look into that a little bit more as we go along, but that's kind of where we want to be going with that. Okay, so next, when I'm just over here on the carbon NMR, the other thing that I do is I just tend to look for how many peaks do I have in kind of my major sections. And just as a reminder, the major sections that we're looking for, we're just doing this with our reference table by our side. We're looking at, I'm just going to highlight them on here. In terms of most common sections that you'll find, or it's going to be these ones that I'm highlighting here. Okay, so those are going to be kind of our heavy hitter sections. And I know that I just didn't circle 2 of them, but the alkene and the alkyne are definitely the ones that show up just less frequently. And I would say this is just all of the carbonyls. Look for aromatic peaks, look for stuff next to electronegative atoms, and how many alkyl type groups do we have. So let's go ahead and use those numbers and kind of apply them to the chemical shifts of our carbon. So let's start with the alkyl region. So 0 to 50. I'm actually going to switch these real quick. There we go. That way I don't have to scroll past the IR page every single time. All right, so 0 to 50, we're looking right here, these two, because I've got 50 right about there. So this is going to be my alkyl carbons. Okay, so I've got 2 of those. We look at the next section, we're looking 40 to 90, and that's going to be like a carbon connected to oxygen, nitrogen, or a halogen. So 40 to 90, we've got 1 right here. Okay, this one is going to be, let me pause this. Glad I checked. I do have a meeting. Okay, so this one right around like 68, because 70 is right here. So that's going to be probably a CO, and I'm picking O because I know that there is oxygen in the formula. So I've got 1 CO bond. Okay, then if I move on to my next section, the next big one is aromatic from 120 to 160. So this guy is a little bit on the edge. It's right on the edge of that 160, but it's like pretty close. So I would say if we're kind of looking at this, this one is just slightly outside of it on the low end, and this one is slightly outside of it on the high end. Oftentimes that's kind of indicated by having both kind of electron withdrawing and electron donating groups, so that you have different areas of shielding and deshielding on an aromatic ring. So this does take some practice, but if you think about this and the fact that Yes, I do have a benzene most likely, as we've seen a couple times already. The aromatic region being spread around kind of makes sense, okay? And we're looking for something, we at least need 6 at the most, but we need at least a few aromatic carbons, okay? Alrighty, so then we have our last section, which is our carbonyl section. Okay, so if I have an ester, amide, or acid, I'm going to be looking 150 to 180. Aldehydes and ketones are going to show up more downfield than that. So where I've got it, I have it right about 168, it looks like. So the 168, that's going to be a carbonyl. So this is either an ester or an acid. Okay. And so when I'm listing those out, I did not put amide on that list because as we're looking at this, I do not have any nitrogen in my formula. Okay, so I'm not going to consider an amide that has to have a nitrogen in it. So already we've got some ideas of what's going on here. So I've got 4 aromatic peaks. I've got an ester or an acid. I've got a carbon-oxygen bond. And when I put those things together, if I'm thinking about acid versus ester, having a CO bond means that I probably have like some sort of alkyl group attached to my oxygen, which makes acid a little bit less likely. But just because we have 3 oxygens and we've got this big old OH here, I'm not quite sure if we're going to have an ether yet and a carboxylic acid or an ester and an alcohol. So we got to figure that out a little bit more. Okay, so now let's look at the proton NMR. So from the proton NMR, we've got integrations, we've got multiplicity, we've got chemical shifts. So we've got a lot of things to think about. The first thing that I would consider here is just how many proton environments do we have? So we've got 1 peak, 2, 3, 4, 5, 6. Okay, so 6 individual proton environments. And keep in mind that the splitting does not change the fact that this is 1 peak. It's just split into a triplet, okay? So let's count the peaks first, and then we're going to identify what the splitting looks like, so then we can figure out how many neighbors we have. So this one, that's a nice doublet. We've got doublet, doublet. We've got another doublet. That's a singlet. I would say it's fairly broad. We've got a triplet. This one is a little bit tough to see because it's not quite the best in terms of split. So that's why a lot of the problems that I'm going to give you in class have this kind of summary down below to kind of show you, like, if I don't have a zoomed in region or anything, so it can show you like that is a sextet. And then we can figure out neighbors from there. And then our final peak is a triplet. Okay, so now that we have some stuff put together, we need to start drawing out some fragments here. So I always like to start off with, if I have an aromatic ring, I start with the aromatic ring. One, because it feels like I get a lot of the carbons out of the way, and you actually get a lot of the structure made once you have that benzene ring figured out. So let's start with the fact that we've got 4 aromatic peaks in the carbon, and then we've got 2 aromatic peaks here. Okay, and I guess we didn't do chemical shift for the proton. Oh, let's do that first. Okay, so I kind of spoiled it. That's going to be our aromatic peaks here. So if we look at the proton, 6.5 to 9 is where we're looking for aromatic. So we've got 6.5 is right here. So what this one is a little bit tricky. But these two are very clearly within that aromatic region. I would say when you're looking at this, you're like, well, is that an aromatic carbon, like H peak? The fact that it's so broad, like broad down here at the bottom, that tells us that it's something else going on. So generally, if you're looking at OH peaks, these variable is because you have such a big range, but also you want to think about the fact that you're going to get a little bit of a broader peak from those like NH-OH bonds than anything else. And if you look at this guy, 4 to 7, the one that we have is at 6.5. So that's probably an OH peak. But importantly, if we look, this goes to about 8.5. So if I was looking for a carboxylic acid OH, we're looking between 9 and 12. Okay. So once I put that together, that I have a phenyl OH, that looks pretty decent, and I don't have this, that means I can go back through and say, okay, it's probably not an acid because I don't have that acid peak in my NMR. And I do have this OH peak. So that OH is probably on a phenyl. Okay, so that's all just kind of putting the pieces of the puzzle together. All right, so let's look at this triplet that's like 4.3-ish, whatever. So 4.3, we're looking pretty much right here, right? So just in that 2.5 to 5, and that's our alpha to oxygen and nitrogen. But in this case, we only have oxygen, so this is going to be alpha, oops, let's not change colors here. Alpha to oxygen. And then these two are pretty much in our, well, I think, well, let's check before I say anything. So alkyl is 0 to 1.5, and then 1.5 to 2.5 is going to be allylic, benzylic, alpha to carbonyl. Okay. So let's check that out. So I have one that could be allylic, benzylic, alpha to CO. So I have some options there, but then this one is most certainly just alkyl. Okay, so now that I have all the information written down, let's build some fragments. So as I was saying, let's start with the aromatic region. So I've got a total of 4 protons on my benzene ring. Okay, and I think I'm gonna have to pause this so that I have my next meeting and then I'll finish it. Alrighty, so I believe where I was at before I had to take my break for my meeting. We were trying to determine the aromatic substitution. So the first thing that I do is you want to look at the total integration of your aromatic region. So in this case, I've got 2H and 2H. 2 plus 2 equals 4. Okay, so this is a piece of information that a lot of people seem to overlook. And I'm not talking about like the simple mathematics. I'm just talking about the fact that if we think about a benzene ring, we draw that out. And we draw in all the H's. There are 6 hydrogens on that benzene ring. Okay, if I end up integrating out to only 4 hydrogens, it seems like common sense, but it's very, very commonly overlooked. I must have 2 bonds to something, right? So that I have now 4. Okay, so that's what I want to be thinking of. So when I'm going through that, I have options in terms of what I actually have on here. So I basically have, I could have 2 of the same substituent on. Actually, we're gonna move this discussion to a different page real quick. Okay, so I could have 2 of the same substituent right next to each other. I could have them 1 carbon apart. Or I could have them on opposite sides. Okay, I could also have 2 different substituents. So I could have X and Y. They could be right next to each other. They could be one apart. Or opposite ends. Okay, so I basically have these 6 options of what I can have, given the fact that I have 4 hydrogens in this NMR in my aromatic region. Okay, so when I'm looking through this, there's a couple things that we're going to think about. So I'm going to go ahead and erase the H's so that we're looking at everything the same. Okay, so all of them have 4 H's here. So we need to go through here and see and figure out, one, how many hydrogen peaks we would see and how many carbon peaks we would see. Okay, that's going to give us a really good indication of exactly which substitution pattern we have here. So if I've got this one, I've got a mirror plane right here. So that's going to be 1, 2, 3 carbons. And we're going to have 2 protons. Okay, and we're talking about individual environments. So if you're not comfortable with that yet, make sure you review the environments video. So the one where they're 1 away, I've got 1, 2, 3, 4 carbons, and then 3 protons. And then this guy is going to have 2 planes of symmetry. So I'm going to have 2 carbons and then 1 proton. Okay, so all of those proton environments are all identical. So we end up integrating 1 peak to 4. All right, so let's go look at the ones where we have 2 different substituents. So on this one, since I have no planes of symmetry, and I'm looking at the one at the top, so we're going to have 1, 2, 3, 4, 5, 6 carbon peaks. And then we're going to have 1, 2, 3, 4 protons. So those are 4 individual proton peaks. All right, same with this one. No plane of symmetry. So we're going to have 6 carbons, 4 protons. Okay, protons here, and then carbons are all the carbons around the ring. So our last one does actually have a mirror plane. So I have a mirror plane just cutting the X and the Y right in half. Okay, and then the 2 sides of the ring mirror each other. So I've got 1, 2, 3, 4 carbon peaks, and then 2 proton. Okay, so then we need to figure out, like, based on these numbers, right? There's only 2 that actually overlap each other completely. So based on these, we can very quickly identify which substitution pattern we have without even looking at integration or NMR, or, well, we looked at integration a little bit, but without looking at the multiplicity or anything like that. So we're looking for, let's refresh ourselves here. So we decided there's probably like 4 aromatic peaks. And then we've got 1, 2, sorry, I didn't mean to select that. Alcohol 1, 2 aromatic protons. Okay, so 2 for proton, 4 for carbon. So our best fit, oh, there we go. It's like, what the heck is going on? Our best fit is going to be that guy. Okay, and if we think about what's going on here, I'm just going to take that picture and I'm going to pull it up here. So if we're looking at this, both of these are doublets, meaning they both have 1 neighbor. So if I draw out my H's real fast. Okay, if I'm looking at HA, I have on this carbon, I've got 2 carbons attached, 1 of which has an H, 1 neighbor. If I look at carbon B, I'm looking at this carbon, go 1 over, I've got carbon A, proton A, and then Y doesn't have anything. Okay, so that means that we're looking at these 2 are going to be our 2 doublets. Okay, so basically what we have right now is we have developed or identified 2 points of connection. Okay, so we have to figure out something here and something here. But the nice thing is we have completely figured out our aromatic region. We've taken 6 of our carbons and 4 of our hydrogens out of consideration here. Okay, so then at this point, let's drop a few of our other fragments. So I'm going to make a list of fragments over here. Okay, so basically what we have, I'm going to do it under. We've got our aromatic ring. Okay, which has 2 connections, and I tend to use squiggly lines for those connections. And then I just know that I need to connect the squiggly lines together. So that's going to be one of my fragments. Let's move on down the list to see what else we can come up with. So we kind of figured that there's probably an ester here because it looks like our alcohol is coming from an OH. So one of those fragments, we're going to have an OH and attached to something. We think that this is probably our aromatic ring, just based on chemical shift there, because it's definitely more downfield than most alcohols are. A lot of times you'll see alcohols kind of around this region, so it is quite far shifted downfield. So that's another fragment. So then we have the 2 oxygens to make our carbonyl, which in this case is probably our ester. So let's take a look at our ester, and I would just draw it up first. Like this is the basic fragment for an ester, right? We've got the carbonyl part, we've got the oxygen part, and then connections on both sides of that. So if we're trying to figure out what is actually connected on those sides, the proton is going to be the best way to go. So we identified this triplet as being alpha to an oxygen. So that means I either have something connected to my alcohol, which would not make it attached to my phenyl, or it's attached to my ester. Okay, so that's the 2 things that we need to think about. So when we're trying to come up with the fragments apart from that, as soon as you see a 2H, I don't want you to be seeing a zebra when it's a horse. If it's a 2H, it's probably just a CH2. Okay, so we're going to consider it a CH2 here. And if I'm trying to figure out how many neighbors are going to be over here, if I have a triplet, that means that I have 3 minus 1 is going to be my number of neighbors. So it's going to be a CH2 with a CH2 next to it. Okay. And we said that it's probably connected to oxygen, so we can put an O right here. And then we have some connection point over there. Okay. If we keep going with some more of this kind of splitting type patterns going on here, so our sextet, that's going to have 5 neighbors. Again, it's another 2H peak, so it's probably a CH2. So we'll start with a CH2. Okay, 5 neighbors is probably the easiest way to get to 5 is going to be a 2 and a 3. Okay, so we can have a CH2 right here, CH3, and so then those 2 H's in the middle are going to have 5 neighbors. And then our triplet over here, so that integrates to 3. So again, we're looking for horses, we're not looking for zebras. The 3H is most likely going to be a methyl. So we're probably going to have a CH3. And because it's a triplet, that means it has 2 neighbors. So we probably have that, where we're looking at this CH3 is giving us that triplet peak. Okay. So if you look at what I have here, I kind of have the same fragment drawn out a whole bunch of times, where I first start off with, okay, this oxygen is influencing the H's right here. Those H's see these H's as neighbors. And because the oxygen's here, it gets shifted to the left. Okay. And then the next one I go, it says, oh, I've got 5 neighbors now. So I have a CH2 and I'm next to a CH3. And then my very end one, I say, oh, I've got a CH3 that's next to a CH2. All in all, what that all adds up to, I needed more space for my fragments. Goodness gracious. We're gonna scooch these guys. Okay, so we're gonna say we've got O, squiggly, and squiggly there. Okay, so we have all those possible fragments here. And that's actually all of my protons, right? So if we're looking at the carbons, what we want to be thinking about here is that I've got 1 carbon connected to an oxygen, 2 just regular alkyl, 1 carbonyl, and then 4 aromatic. Okay. So I might actually have all of the atoms covered right now. I just need to figure out how they are all actually getting put together. Okay. So I'm going to take this to a new page so that we can have some space to work with them. Yeah. Okay, so these are our original fragments. So what we were looking at before, we have 3 pretty clear like alkyl peaks. They might be next to oxygen. They might be close to other things, but we're looking at stuff that is probably 3 alkyl peaks, at least like sp3 carbons, right, with hydrogens on them. So one of the things that we said was that these all kind of seemed connected in a way where they're all just kind of like building off of each other. So what we might be able to see here is we might be able to just add these all together. To get to that structure. Okay. And that's something that part of it comes with practice, part of it comes with just being willing to take a guess and see what happens. So the whole process that we're doing here, what we can't guarantee that we're going to be making, like we're going to be drawing the right product right off the bat. We need to be a little bit more comfortable with kind of like trying stuff out, doing guess and check, going back and looking at your data and see if it fits. Okay, that's what we're aiming for. So we might be able to get away with putting all of these fragments into one piece. So we also said that we might be able to just stick our alcohol on our benzene ring. Because based on the chemical shift of the alcohol, that seemed to make sense. Okay, so we would still need one of the other pieces to go in here. Okay, so at this point, if we have a situation where we're looking at this as being our only leftover piece, we've got this kind of combined piece, right? We've identified that that CH2 is here. So at this point, we've got 3 pieces that we need to put together. So I would say another very reasonable, we're gonna drop 2 reasonable options. Okay, so this is possibly attached to an oxygen. We could also think about, is it attached to a carbonyl? Okay, so we're gonna drop a couple options because at some point you have to have like your pieces around your fragments that have more connections on them. So let's draw up a couple options. Okay. I would say these are two very reasonable options. So if we had considered like, okay, maybe that is, because we're at some point we still have like this kind of piece involved. So, and we would see, you know, some downfield shift being alpha to the carbonyl like that. So when you've got a couple of options, what you want to do is go back and look at the data and see if it makes sense. Okay. So if I'm looking at option 2, all of my splitting makes sense. Okay. I still have a CH2 that's a triplet, a CH2 that's a septet, a sextet, and a CH3 that's a triplet. Right. So I still have that one, that one, that one. The integration all works. The splitting all works. The only thing that it does not quite fit is if we look at the chemical shift here and we compare it to the chemical shift here, it's around 4. And if it was alpha to that ester, it would be not even past 2.5. Okay. So that's the kind of like subtle things that we want to be able to pick up from chemical shift situations where we would expect this CH2 to be more upfield than 4. Okay. But this one we would expect to be about 4. Okay, each of them have our phenol on it, so the OH on the benzene ring. We've got the 2 doublets from our benzene. We've got the triplet, the sextet, the triplet. So one last thing that I like to do is to go ahead and assign the peaks. Actually, I'm just gonna assign the peaks and see if it makes sense. So we're going to do 1 for proton and we're going to do 1 for carbon. All right, so starting with the proton, let's do the alkyl chain first because that's easier. Okay, so the first one is a CH3. So we're going to label these A, B, C. Okay, so peak F is going to be that methyl on the end there. Okay, peak D is going to be the one that's closest to the oxygen that's feeling more of that electronegativity. So that one's going to be D. E is going to be our sextet. Okay, so then we also have this H is C. Now it can be a little bit tricky to decide between the protons on the ring, on an aromatic ring. So what we're really looking for here is resonance is going to help tell us what's shielded, what's deshielded, and all of that stuff. So if we're looking at this, we're taking away electron density towards that towards that ester. So we're gonna actually end up with delta plus and delta plus right next to those. Whereas these lone pairs are gonna donate electron density in, thereby shielding those two. Okay, so in that situation, with this delta minus, that delta minus, then we're looking at the one that's most de-shielded, the most positive, is going to be A. And the most shielded or negative is going to be B. Okay, so that's all of our protons. A lot of times I don't necessarily look that carefully at how you assign your aromatic peaks, but that's how you would do it. So in this case, for the carbon, we're going to go with the easy ones first again. So this is going to be our peak at 168. Oh, wait, let me just do 1, 2, 3. Oops. Okay, so 1 is going to be our carbonyl. Okay, 6 is our carbon connected to our oxygen. And then 7 and 8, those are generally as distance comes, you're going to go farther away from the O, you're going more upfield. So this is going to be 7, and this is going to be 8. And then we need to deal with the carbon peaks in the aromatic ring. So one thing that's a nice little trick here is integrations in carbon do not technically exist, but you can use the height of the peaks to give you a good indication of kind of how many carbons are in that environment, for instance. So there's a couple things to keep in mind here. So carbons without H are the shortest. Okay, carbons that have H's on them tend to be taller. So if you look at like these ones that are all CH2 or CH3, we're going to use that as kind of our one carbon line-ish. Okay, so if you look at 3 and 5, they're about twice as high. So these have 2 carbons, 2C, 2C. All of these are 1C. Okay, I'm going to do those in different colors. That's going to be confusing. So we've got peaks that are kind of twice as high when we've got multiple carbons involved or 2 carbons involved. And then we're going to use this as kind of our metric for what a 1 carbon with hydrogens looks like. And that kind of gives you an indication of why these guys are so shrimpy. So when we don't have those protons around, that signal becomes a lot smaller. So these are all going to be our carbons without hydrogens on them. Okay, and they're all 1 carbon each. So that kind of helps tell us like 2 versus 4, it's going to be one of these guys. Okay, so if we're looking at that, in this case, since we're attached to the most electronegative atom, we're going to have this one is going to be 2. This one is going to be 4. Because we are next to a delta plus here, but this carbon being right next to oxygen, that is getting an direct electron withdrawing effect because the oxygen is electronegative. Yes, it is donating electron density in, but it's mostly landing over here, like 1 away. All right, so then we have to figure out 3 and 5. We kind of already talked about the delta plus, delta minus for those 2 situations where we've got 2 equivalent carbons in each case. So we're going to use the same kind of idea where these are going to be delta plus. So those are going to be our more de-shielded ones for 3. And then our more upfield ones at 5. And so that's how I would assign it. I will say I don't necessarily expect you to be this precise with them. If you just have kind of, like usually when I'm looking for these, I'm looking for stuff like, did you assign the carbonyl correctly? And like the stuff connected to oxygen, kind of the big ticket items, not necessarily the nitty gritty of assigning the carbons on your benzene rings. But that's for class. So as always, let me know if you have any questions. This is the final answer. Hopefully that kind of shows you a little bit about the process that I go through. I might try to make another video where I use a table if you don't like this kind of freeform style. I like the freeform, but I know some people don't. You can also set up tables and stuff for yourself to kind of guide yourself through the process. So let me know if you have any questions, and I will see you all later.